6.1 talks about inner products. Now the inner product is nothing more than the dot product. So just keep that in mind. The notation is kind of awkward how they write it. So recall that I've been using this for vector notation. So if I want to say AI plus BJ, I've been writing AB, where these are constants. They're the coefficients of those I and J, you know, or the I component and J, however you want to see it. But now they're using that notation on this is vectors. And that notation right there means the inner product. So what's the inner product? It's nothing more than the dot product. So if I take U V, that's simply U dot V. So let's read this definition. Now it should make sense. The inner product on a real vector space V is a function that associates a real number. Remember, this is the dot product, which is going to yield a scalar, with every pair of vectors in V in such a way that the following axioms are satisfied for all U, V, and W in that vector space and all scalars K. Well, obviously, if you take U dot V or V dot U, it makes no difference. If you take U plus V dotted with W, you could take U dotted with W, V dotted with W, and sum the results. If you multiply one of the vectors by K, then you could simply say when you multiply them, well, hey, take the dot product and multiply the results by K. And if you take a vector dotted by itself, remember that's defined as the magnitude. That's always bigger than or equal to 0. The only time it would be 0 if the vector itself is 0. And a real vector space with an inner product is called a real inner product space. So recall that. Here's the definition of the inner product of U and V. It's basically U dot V and the tradition. Now they're going to add weights. Weights is kind of like how much does each of those component weight, kind of like percentage, sort of like GPA, you know, an A weighs 4 points, B weighs 3 points, and so on and so forth, and it depends on each unit. Now the rest is going to all make sense, hopefully. Let V, if V is an inner product space, then the norm is nothing more than the length, and we know how to find the length of a vector, right? If I had vector V being AB, then the norm of that is simply A squared plus B squared. Well, now if I want to take the norm of the vector, well, that is the square root of V multiply the dot product of V times itself. And remember how that works. If V is A dot B, then it's going to be V dotted with V, and that's going to be A squared plus B squared. Nothing new. And the distance, find this first, right? Then dot it by itself, and that gives you the distance. A vector of normal 1 is called a unit vector. So take any vector divided by its magnitude, or in this case, by its length, you'll get a norm vector. And some definitions right there. Now, I don't think we're going to get to definition 3, but just in case, depends on how long it's going to take. If U and V are vectors in the inner space vector V, and if K is a scalar, then the magnitude of V is bigger than or equal to 0. Again, unless it is 0 itself, then it will equal 0. If you take K, the magnitude of K, V, you just take the magnitude of absolute value of K times the magnitude of V. That will work. If you take the distance from U to V, that's the same distance from V to U. And again, the distance is bigger than or equal to 0, right? With equality, it will equal to 0 if and only if U and V are equal, which means you're at the same point. And I'll point those out as we do examples. Now, if V is an inner product space, then the set of points in V satisfying the magnitude of U equal 1, we did that way back. That means if you run in all directions with a radius of 1, in 2 dimensions you create a circle with a radius of 1. And if in R3 that would be a sphere. We did that on one of the homeworks. let's look at a problem. And again, the difference between what we did before, you might be thinking, wait, but we did the unit, we did the dot product, why are we doing it again? Because now we're doing weighted. So the weight on the I component is different than the J. And in this case, and I'm going to show you an easy way of doing this. Take U dot V. Well, U dot V is simply U1 V1, right here. Let me write it out. If U is U1 U2 and V is V1 V2, these are components. If you take U dot V, shouldn't that be U1 V1 plus U2 V2? So that's the tradition. Now they're going to add certain weights on the I and the J. All what you have to do is do that at the end, and let me elaborate on some of these things that I said I'm going to show you, meaning the distance, the magnitude, the order you could do that in, a constant times, and definitely U minus V. Well, U dot V is simply, use black color. So this is supposed to be, there's U, there's V. That's supposed to be 1 times 3 and 1 times 2. But what you're going to do, you're going to add those weights. You're going to add the 1/2 and the 5. And of course, you're going to add that. So 1/2 right there. All of these are multiplied. I should have used parentheses. That makes life easier. Okay. Here. Let's go the easy route. So that's going to be 1 times 3. And that's going to be 1 times 2. I'm going to add the weight. I'll do that at the end, which is 1/2 right there and 5 right there. And what that will be is 3/2 plus 10. That is 10, 20, 23 over 2. So as you see, the inner product is a scalar. And here, if you take K, well, let's make sure we get that as well. KV, well, K in this case is a 3. KV, right? Dot it with W. Well, K is a 3. Well, wouldn't that be 9 and 6? And you're going to add the weight on each of those. And the weight here is 1/2, and the weight here is a 5. And that will be 0 minus 30, which is negative 30. So nothing, again, we're going to apply this. It's going to be a straightforward section if you just follow the tradition of what we're doing. Now, if I want to do here U, so if I go ahead and add a 1/2 automatically, U plus V. U plus V is 1 plus 3, and you're going to dot it with 0 plus 5, and it's going to be 1 plus 2. Dot it with a negative 1. So altogether, you're looking at a 0 plus 5 times 3 times negative 1. That would be negative 15. Again, not even busy work. It's really simple work. We just want to define that for vectors, we want to define it for matrices, and define that for polynomials, and pretty much that's it. Magnitude of V, well, we know what that is. That's really V, right? How do I write that? Let's go this way. That is the square root of V dotted with V. And what would that be? Well, if we're only talking about V, again, V was 3, 2. So that's going to be V3 dotted with 3, a half, and 2 dotted with 2 and a 5, and whatever that is. And that's how we're going to do all of those. That's going to be 9 halves plus 10, 20. So that would be the square root of 20, 40, 49 halves, or 7 over radical 2. If I want to find the distance from U to V, well, distance from U to V, let's take U minus V, right? That's a distance. What would that be? That would be, U was 1, 1, I think. 1, 1, and 3, 2. So U is 1, 1, and 3, 2. That's V. That would be 3. That's a negative 2. 2 minus 1 is 2 minus 2. U minus V. That's a negative 2, negative 1, or 2, 1, however you want to see it. All right? And if I take the distance of that, that's going to be the magnitude of this. That's going to be the square root of negative 2 times 1 half, and negative 1 times 5, and you add those. So that's going to be the square root of 2 plus 5. That's the square root of 7. And if I take U, which is 1, 1, minus K was 3, I believe. V was 3, 2. I'll get pretty much 1 minus 9, which is negative 8, and 1 minus 6, negative 5. Hopefully, if I make a mistake, you get the point. The magnitude of that will simply be the square root of negative 8 multiplied by a half, and negative 5 multiplied by a 5. And you add those. And that's going to be the square root of 32 plus 125. What is that? 725, 157. All right, again, not that hard, just trying to get used to it. Now, what happens if you bring a matrix in? Well, if you write the vector as a vertical vector, the inner product of an n by n matrix, well, if you're given U and V, it will be AU dotted with AV. That's also a scalar. And if you take this is not going to come back until some problems. The standard Euclidean and weighted Euclidean inner products are special cases of matrices of matrix inner product. The standard Euclidean inner product of Rn is generated by an n by n matrix, right? And U dot V is, as you see, multiplied by each weight. Now, to generate the matrix that does this, what you do, you go on the diagonals and you would use the square root of those weights. The reason for that, when you multiply it by itself, that will clear and give you that weight. Dot it with U and V, U1, V1, U2, V2, and that's how it works. So this can be seen as observing A times its transpose, which is n by n matrix, whose diagonal entries are the actual weights. When I get there, I'll talk about this a bit. Now, there's a long way in the shortcut, but this is the shortcut. Let's look at how do we play with, how do you apply the inner product to matrices. So compute the quantities A through F of exercise 1. Again, the same thing that we did. And now we're going to apply the inner product on this matrix. Remember, everything is the same. U, V. Well, if I'm talking about U, V, that's going to be, let's see, A, U, and we're going to dot that with You see it right there. AV. We're going to dot that with, and V was 3, 2. And that would be, let's see, 1 plus, so that's a 1 by 1, a 2 by 1, right? Okay, that keeps on happening. Sure. That is 2 by 1. So that will be 1 plus 0, that's 1. 2 minus 1 is 1. And I'm going to dot that with 3 plus 0 is 3. And 6 minus 2 is a 4. And what is that? Again, think of them this way. 3 plus 4 which is a 7. And nothing more than practice. And if I wanted k, well, I know k is 3, right? So here I'm looking at 1, 0, 2, negative 1. Dot it with kv. kv, since that's 1, 1 times 3, that's 3, 3, nothing more. And I'm going to dot this with 1, 0, 2, negative 1. And I'm going to dot that with w. And w is, oh, v, not u. I'm sorry. It says kv. V is 3. So multiply by 3, that's 9, 6. And I'm going to dot with 0, negative 1. So do this first. That turns out to be 9 plus 0 is 9. And 18 minus 0 is 18. Oh, that's a 6, not an, oh my goodness. Okay, 9 plus 0, that is 9. And 18 minus 6 is 12. And I'm going to dot that with, here we have 0, 0 plus, and that's going to be 9 times 0 plus 12 times 1, which is 12. All right. And it turns out the first couple of problems are the longest. And how about here? Well, the same deal. I'm going to take a 1, 0, 2, negative 1. And if I take u plus v, what would that be? U plus v, 1 plus 3, that's a 4, 3. And I'm going to dot that with 1, 0, 2, negative 1. And w is 0, negative 1. And this turns out to be 4 and 8 minus 5. Dot it with 1 plus 0, 0 plus 0 is 0, and 0 plus 1 is 1, and that turns out to be 0 times 4 plus 5 times 1, which is 5. And if I get to these parts, if I want to take the magnitude of v, well, first I'll figure out what that is. Well, guess what? It'll be the square root of v. Well, v is 1, 0, 2, negative 1 multiplied by 1, 1, right? Dot it with the same thing. And that is 1 plus 0, that's 1, 2, the same thing. And that's going to be the square root of 1 plus 4, which equals radical 5. There we go. And if, oh, it's v, not u. That should have, okay. Suppose that's u. My mistake. What if I want to find the distance between u and v? Well, hey, how do we do that? We do the same thing. We'll take the square root of, and how do you find u minus v? Well, guess what? So u minus v, that's simply 1, 0, 2, negative 1 u, which is So that will be negative 2, negative 1. There we go. And we're going to dot that by 1, 0, 2, negative 1, dotted with negative 2, negative 1. And that's going to be the square root of, let's see what that is. That is negative 2, negative 3, dotted with negative 2, negative 3. And that is 4 plus 9, which is radical 13. And if we take this, again, figure out what that vector is. What is that? If I take 1, 1 minus 3 times 3, 2, that is simply 1 minus 9, negative 8, and 1 minus 6, negative 5. So when I apply that, that's going to be the square root of, and I'm going to take 1, 0, 2, negative 1, negative 8, negative 5, right? Dot it with 1, 0, 2, negative 1, negative 8, negative 5. And that's going to be negative 8 and negative 16 plus negative 16 plus 5, negative 11, if I'm not mistaken. You get the idea. And that's going to be the square root of 64 plus 121. That's the square root of 185. All right, again, the number 1 and 2 are going to be the number 1 and 3 are going to be the busiest work for us, but it's good to get those out of the way. Now, let's talk about what this is. Find a matrix that generates the stated weights. So remember, if you looked at those and you really recalled what we did, we multiplied by this matrix every time. What we want to create a matrix that has the weights, where you do the dot product regularly. And all what you have to do is multiply by that matrix. Well, according to what we wrote up there, now let me elaborate. If you just want a matrix with the weights, just put the square root of each weight into the identity matrix. This is a 2 by 2. So if I wanted to really get the weight of this, I'll simply say there it is. And that's all I had to do. Really simple. Nothing to it. So find a matrix that generates the stated weights. There it is. And we'll come back to this. We're going to redo this one more time, but slightly different. How about this problem? Use the inner product of R2 to generate the matrix A to find UV, where U is given as 0, negative 3, and 6, 1. Well, okay. What do you think UV is? Well, the tradition. That is simply 2, 1, negative 1, 3. U is 0, negative 3. Here there are no weights. Dot it with 2, 1, negative 1, 3. And V is 6, 2. And that would be, let me just get that right. That is 2, negative 9. That's not 2. Okay, come on. My mistake. That's 0 minus 3. Negative 3, negative 9. And here you'll get 12 plus 2. That's 14. And 6 and a 0. And that would be, what? Negative 42. That's it. Plus 0. Negative 42. Done. So we just want to make sure we get that out of the way. It's not hard at all. Now, if I wanted to find, so suppose we're talking about the vector U is represented by a matrix, and vector V is represented by matrix V. Those are matrices in the vector space M, N, N. Then the formula for U dot V is the trace of these matrices. So as you see, if we have matrices, no vectors, compute the standard inner product for M22. Okay, well, this is simply the trace of, let's see, U transpose, I'm going to write it. That's good. The inner product of those would be the trace of U transpose V. I should make those bigger because they're capital letters. Okay, well, what is that? That is the trace of, and let me take the transpose of U. The transpose of U is 1, -325 and 4608. What would that be? That would be 4 plus 0, which is 4. That would be 6. 6 minus 18 is -12. That would be 8 plus 0, which is 8. And that would be 20. That would be 12. 12 plus 40, 12, 52. And the trace of this would be simply 4 plus 52, which is 56. And there it is. And now we're going to do this on polynomials. It's kind of straightforward, really. If you're doing two polynomials of same degree, PQ will simply be the inner product kind of on the matching coefficients. So you know that the constant, and the magnitude of P. If you just apply P, squared, 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 all the components. If you're evaluating those P and Q at x naught, well, evaluate it at x naught and do the same exact thing. Apply the constant, the linear, and go on all the way up. So in this case, find the standard inner product of P2. P2 is a second degree polynomial. If I want to find PQ, that would be -5 times 3 plus 2 times 2 plus 1 times -4. And if they give it weights, you add the weights. That's -15 plus 4 minus 4. That's basically -15. Really straightforward. You just want to get used to this new notation. Let me just adjust those. Okay, now we're going to recap this really quick. We're going to redo what we did, but one more time. A weighted Euclidean inner product of R2 is given by the following vectors. Here they are. Find the matrix that generates this. Well, again, to find the matrix that generates the weights, it's a 2 by 2. You simply take the square root of that and the square root of that. And that's basically the shortcut to figuring that out. Nothing to it. If I'm given polynomials, now the difference between this and what we did up there, these are evaluated at the following points. Not a problem. Figure out what P of x sub 0 is. Well, if you put -1 in there, isn't that a -1 minus 1, -2? And if I put Q of x sub 0, which is -1, that is also, that's 2, right? And if I take P of x1, that is 0, Q of x1, that is 1. And if I look at P of x2, put a 1 in there, 1 plus 1, that's 2. And Q of x sub 2, if I put a 1 in there, that's also a 2. And if I take the last, which is P of x3, if I put a 2, 8 plus 2 is 10. And Q of x sub 3, that is 4, that's a 5. And now if we say, hey, can you find PQ? Well, that's simply -2 times 2 plus 0 times 1 plus 2 times 2 plus 10 times 5, whatever that is. And that turns out to be -4 plus 0 plus 4 plus 50. So that's just 50. And there it is. A lot of adjustments to make. That's okay. All right. And what do you think they're asking? I went back to this weighted vectors again. Not a problem. They want us to find the magnitude of U. Well, the magnitude of U is simply the square root of the inner product of U with itself, right? and that is, let's see, actually let me go here, the square root of u. Negative 1 times negative 1 and 2 times 2, but there's a weight. So we're going to do a weight of 2 and a weight of 3, and that turns out to be the square root of 2. What is that, 12? So that's radical 14. Again, simple calculations. They want us to find the distance from u to v with the weights. Forget the weights. Let's do u minus v. What would that be? That would be negative 1 minus, that's negative 3, and 2 minus 5, negative 3. So that would be the square root of, oh, they're all the same. You're not going to tell the difference. So negative 3 times negative 3 and the j component, but you're going to add the weighted to them. That's going to be a 2 right there and a 3 right there. And that's going to be the square root of 918. What is that? Plus 27. So that's the square root of 1835. 30, 40, 45. You know, if I make a mistake in addition, but you understand. And of course, you can use a calculator, but here we are. You could reduce that if you want. That's really 3 radical 5. It doesn't really matter. Okay, and here we are one more time. Let's look at how this works. Find the magnitude of p, just p by itself. If I want to find the magnitude of polynomial p, well, that is the square root of the inner product of p with itself. I don't know if I should put an arrow on that, I suppose. Okay, and that would be what? That would be the square root of negative 5 times negative 5, 2 times 2, and 1 times 1. And that's the square root of 25 plus 4 plus 1. That's square root of 30. And then they ask for, find the distance from p to q. Well, to do that, I need to figure out what p minus q is. And again, how do you do that? You look at the components. Just if you combine those, wouldn't that be negative 5 minus 3? That's negative 8. Plus, okay, I'm going to write it just for the notes, 0x, and x squared minus, that's 5x squared. And if you want to find that, that's simply the square root of negative 8 squared. And again, just for the notes, I know 0 doesn't change anything. And what is that? That's the square root of 64 plus 25. That's the square root of 89. All right. You know, just a couple more to go. Just making sure we're really getting used to this. If you remember what this was a trace of u transpose v. Well, what's u transpose v? Okay, and that's gonna be 1, negative 325, and a 4608. So that's gonna be 4 plus, that's 4, and that's 1, 6 minus 24, 6 minus, oh, I didn't see that, my mistake. It's asking for this. Okay, sorry about that. I think I saw that. So what is that? 1 plus 9, that's a 10. And that is 2 minus 15, that's negative 13. And that will be 2 minus 15, negative 13. And that will be 4 plus 25, 29. So the trace will be simply, you're looking for the magnitude. And that is the square root of 39. So that's how we do it with matrices, right? this. Oh, and they want the distance from U to V. Okay, good thing. Now I see it from U to V. If I want it from U to V, what is U minus V? That would be U minus V, -3, -4, -3 and 5 minus 8, -3, if I'm not mistaken. So d of uv would be the square root of the trace, and you're going to multiply. Let me see how this works. -3, -3, -4, -3, -3. So that transpose, right? The transpose of that. Okay, and what is that? That is the square root of the trace of, and let's see what that is. That's 9 plus 9, 18, 12 plus 12, no, 12 plus 9. 12 plus 9 is 21, and 12 plus 9 is 21, and 16 plus 9 is 25, and the trace of that is what? 18 plus 25, that's the square root of 30, 43. There, that's how you do it with matrices. Almost done. Coming more problems. Here we go again. Let's see if we can get this one correct. We don't have to write them out. We can do them as we move on. So if I want to find the magnitude of P, that is simply the square root of P. Well, that's the square root. P at -1, you get -2, right? Squared. At 0, you get 0 squared. And at 1, you get 1 plus 1, which is 2 squared. And at 2, you get 2 plus 8, which is 10 squared. You get the square root of 4 plus 4 plus 100. That is the square root of 108. I think that reduces 2. And yeah, you could take the 2 out of it, but it doesn't really matter. You get the idea. And if I want to find distance of PQ, well, let's figure out what P minus Q is. P minus Q is going to be, let's see, at all of these values. Okay, I'm going to subtract them. I'll put them in here one shot. Square root of, if I put a 0 in, I'm going to get 0 minus 2 squared plus, I'm going to get, if I put, oh, never mind, I put 0. My mistake. Forgive me. Okay, if I put -1, that's -2 and a -1 minus 2 squared. If I put 0, now I'll get 0 minus 1 squared. If I put a 1, 1 plus 1 is 2 minus 2 squared. And if I put a 2, I'll get a 10 minus 2, 4 plus 1 is 5 squared. So I'm looking at the square root of -16 plus 1 plus 0 plus 25, square root of 17, 25, 35, 42. All right, just one more to go. And what if I wanted to apply this on the matrix? There's U, there's V. I want to find the magnitude of U. Well, the magnitude of U is simply 1, 2, -1, 3 multiplied by -1, 2. Dot that with itself. square root. That is the square root of, and what would that be? Negative 1 plus 4, 3, and 1 plus 6, 7. Dot it with 3, 7. That will be the square root of 9 plus 49, the square root of 58. You can take a 2 out of that. That will be 26. You could probably reduce that, doesn't matter. And if I want to find the distance of UV, well, I have to take U minus V, which is negative 1 minus 2, that's negative 3. 2 minus 5 is negative 3. And now what I'll do, I'll say that's the square root of U minus V. So that is 1, 2, negative 1, 3, negative 3, negative 3. Dot it with 1, 2, negative 1, 3, negative 3, negative 3. There it is. And that's the square root of, let me see, negative 9, that's negative 9, 3 minus 6, and 3 minus 9, negative 6. Hopefully I didn't make a mistake. 81 plus 36, whatever that is. That is 7, 117. Alright, and that's pretty much all there is for this section.